I've worried for some years now about the impact that artificial intelligence will have on science. Because many, if not most, research areas are already struggling with nonsense research and flailing peer review, and things are getting worse. The crazy tariff formula of the Trump administration, for example, has widely been suspected to have been AI generated, but I guess it's okay because the UK Tech Secretary too has used ChatGPT for policy advice. Terence Howard, the actor who believes that 1 × 1 = 2, recently put forward a supposed solution to the 3-body problem, almost certainly also AI generated. And I've now received half a dozen theories of everything that were, by admission, written with the help of AI. But that's only the tip of the iceberg, because AI is about to swamp the science literature. In January 2025, a group of economists demonstrated that current generative AI can rapidly mass-produce finance papers. They let GPT and Claude analyze stock data and generated 288 complete papers. These are not AI gibberish papers. They ran a reasonable protocol that analyzed real data. You could do the same in, say, cosmology or particle physics. Take some existing data set and analyze if it supports some dark matter model or the modified gravities of the day. You could generate thousands of papers about this on the snap of a finger, and people will do it, because it's how they earn money. We know that even the early versions of GPT and Claude were used to produce junk papers, fairly easy to track just by searching for phrases like "as of my last knowledge update." Just in January, a group of researchers reported that such AI-generated papers are most common for research on fish. If there are any fish in the audience, please let us know what's up with that. But generative AI has much advanced, and there are no obvious text markers anymore. Just in January, the company Proofig, that specializes in the detection of image manipulation in scientific publications, reported that AI is now so good that in a test they did, most researchers couldn't tell apart the AI-generated scientific images from real ones. This is a huge problem in research areas where images are used more commonly than data series, such as most areas of biology and some of material science. There are other reasons that we can be pretty sure AI fraud is getting increasingly common. For example, the strange story of vegetative electron microscopy. What is vegetative electron microscopy, you might ask? It isn't anything. Yet this expression has appeared now in more than 20 scientific papers as a label for images taken by scanning electron microscopes. Probably, if the images are even real. The phrase seems to have first emerged in a 1959 2-column articles where vegetative cell wall appeared in one column and electron microscopy in the other. So if you read across columns that gave vegetative electron microscopy. Once the phrase existed, it was probably picked up by AI, helped by the fact that in Farsi the word for scanning is almost exactly the same as the word for vegetative. It's now appeared in papers published by journals from major publishers. You might say, these are just some funny anecdotes, but I think we can't dismiss this so easily. These are the cases that we happen to know of, because there was something weird about them. But chances are that by now, the vast majority of AI-generated scientific content, reasonable or fraudulent, goes undetected. Yes, there is an increasing number of people working on identifying this stuff, but, well, that's running into problems too. PubPeer is a platform where researchers can post papers and discuss potential problems. This is widely used, especially in the life sciences. The problem is that, much like with fake reviews, you can abuse this system to make perfectly fine papers look suspicious. Sylvain Bernays, a researcher investigating scientific misconduct, recently stumbled into this. He received an email saying, "Hey professor, I don't like this group of researchers. Can you help me retract these papers? I'll be happy if the first author loses his job." And after Bernays didn't respond quickly enough, followed up, I'm waiting for your response. If not, I'll put all your papers on PubPeer in order to obtain their retractions. This is like leaving fake one-star reviews to make your competitor's restaurant look bad. Finally, if you remember that a few months ago we talked about the cat with academic citations that were generated by uploading fake papers to ResearchGate that were then indexed by Google Scholar. Yes, that cat. Possibly tenured by now. Well, in a preprint that appeared in March, a group reports that they encountered a cluster of authors who boosted their citation count with this very method. In other news, ResearchGate recommended that Geoffrey Hinton checks out a paper that he wrote with Jan LeCun. This collaboration was news for both of the supposed authors. What all this means is that we're nearing the point where science will drown in AI slop. This may not be entirely a bad thing, because it might force scientists to finally do something about their publish or perish culture. But the way it currently looks, the future of science isn't about finding truth, just about generating statistically plausible sentences about it. Imagine we live inside a computer simulation. Wouldn't bad programming explain a lot? This simulation hypothesis has been discussed in physics and philosophy for a few decades, and it's annoyingly hard to get rid of. It's not entirely untestable either. You'd expect clues hidden in the way nature works, because only some laws of nature can be run as computer simulations. In a recent paper, a physicist has now claimed that one such clue is gravity. Yes, gravity might be a computer simulation. Really? I've had a look. In the new paper, the author Melvin Vopson argues that gravity can be explained by the idea that the universe is built up of discrete units like a computer, and that information distributed over these units decreases. That's the opposite of the second law of thermodynamics, which says that entropy can at best stay constant, but normally it increases. The author calls his idea that information decreases the second law of infodynamics. He suggests that, quote, gravitational attraction manifests as a requirement to reduce the information entropy of matter objects in space. In other words, objects fall towards each other because that's what it happened in a system that's trying to minimize the complexity of the information it has to store. He goes on to derive Newton's law of gravity for a point mass. Newton's law is, of course, strictly speaking wrong, in that we know gravity needs general relativity, but then again, Newtonian gravity is a good approximation in many cases, so one could see this derivation as a start. The idea seems closely related to Eric Verlinde's 2011 idea that gravity is an entropic force. That is, gravity is just a consequence of the increase of entropy. Verlinde too only looked at Newtonian gravity. When Verlinde's paper came out, I spent quite some time on trying to make sense of it and eventually concluded that it's mathematically correct. You can reformulate gravity so that it resembles the statistical description of an ensemble of something with entropy. However, it doesn't tell you what the microscopic underlying thing is. Verlinde seems to have had strings in mind. Vopson says he knows how the underlying microscopic theory looks like. All you have to do is to assume that, well, the universe is a computer, basically. Space is made up of discrete chunks like pixels, and everything below the scale of the pixels can no longer be resolved. So according to his idea, if you compress things, information decreases. He explains the basic idea as follows. Imagine space is made of discrete Planck-sized cells, each capable of storing a single bit, either 0 for empty or 1 for occupied by matter. He now distributes these particles across space and uses his equation to calculate what he calls the information entropy. He claims that this information entropy is smaller the fewer 1 bits there are. So assuming that information entropy decreases, therefore explains why the bits, which are the matter, clump. That sounds reasonable at first, but think about it somewhat more and it makes no sense at all. For one thing, you should get the same entropy or information if you swap out the ones and zeros. So you could take that to also argue that matter wants to spread out. Neither of these is correct, because we know how to calculate the entropy and information for the distribution of bits. And it's simply not how the author claims. The entropy is maximal if there are approximately the same numbers of zeros and ones. And in this case, the information is minimal. This is because in this case there is the largest number of possible microstates. Thus, if you'd postulate that information decreases, you'd expect matter to spread out up to some point, which is simply not what we see. This, incidentally, is totally unsurprising, because gravity indeed gives the appearance of decreasing entropy. The way that physicists normally resolve this is by assigning entropy to gravity itself. That is, if matter clusters, that decreases the entropy of the matter and increases information, but it increases the entropy of gravity, so thermodynamics checks out. This paper has multiple mathematical problems, and I think it shouldn't have been published. That said, let's not throw out the baby with the bathwater. Just because this particular idea for how to get gravity as an entropic force doesn't work, doesn't mean it can't work. But I'm afraid this means that we can't blame a programmer that the paper was published. Annoyed by the noise that your laptop fan is making? You're not alone. But don't despair, in the future your laptop might be cooled with lasers. Yes, lasers. Let's have a look. We live in the age of computing, there's no doubt about it. That computers can read and analyze huge amounts of data, produce sophisticated models, and now use artificial intelligence is driving progress across all disciplines. But for half a century, the increases in computing power have relied on Moore's law, the ability to pack an ever-increasing number of transistors in microchips, making them increasingly powerful. And Moore's law has been declared dead a few times in the past years for a simple reason. The smaller you make transistors and the closer you pack them together, the more difficult it becomes to cool them. The overheating of microchips is currently the biggest hurdle on the way to further miniaturization. Traditionally, cooling microchips works by blowing air over them. Some newer designs envision small fluid channels enveloping the transistors to more efficiently transport away heat. But those channels would also make the chips larger again. And fluid channels have limits in how much they can be miniaturized themselves. So this seems unlikely to help much. The heat is not just in the way of continuing Moore's law, it's a problem already. According to a study from Berkeley Lab, up to 40% of the energy that data centers consume goes just into cooling. And as chip designs push for higher transistor density and performance, the cooling challenge gets worse. Almost all supercomputing clusters are now liquid-cooled, but there's only so much heat that liquid can carry away. I don't even want to know how many megawatts we collectively burned by Ghiblifying our holiday photos. Enter lasers. Yes, lasers can be used for cooling somewhat intuitively, because when I think cooling microchips, my first thought is definitely at lasers. But upon second thought, this has been done in physics research for a long time. It's called laser cooling, and indeed there was a Nobel Prize for it in 1997. Laser cooling works by bouncing light off particles so that the light carries away net energy. It usually works by tuning light to an atomic or molecular transition. The light gets absorbed but re-emitted with higher energy. That gradually reduces the average energy of the atoms, so it reduces the temperature. Laser cooling has allowed researchers to study quantum effects more precisely, build highly accurate atomic clocks, and confuse grant reviewers. But this method of laser cooling can't be directly used for microchips. For one thing, it typically requires isolated atoms in a vacuum, but also it makes use of very specific atomic transitions that just aren't available in a standard semiconductor chip. However, scientists have come up with a variant of laser cooling that can be used for semiconductors. It's called resonant damping. Resonant damping is what you do if you slow down a swing without dragging your feet on the ground. You accelerate in the opposite direction of where you're going, effectively taking away energy. Resonant damping for a microchip basically works the same way, just replace the swing with a semiconductor and yourself with a laser. Easy enough. To cool something with resonant damping, you direct laser light at a hot spot in the material and tune it to a frequency that encourages the material to emit more photons than it absorbed. This will carry heat away as light, so it cools. And this isn't just a theory. Sandia Labs in the United States is pursuing this method in collaboration with Maxwell Labs. According to the website, Labs is developing a laser cooling prototype expected to yield 200% performance gains on the latest NVIDIA and AMD hardware, with a 40 times efficiency improvement compared to liquid cooling using the same net power. Those are stunning numbers, but they're not totally unreasonable. Lasers aren't exactly known for being energy efficient, but the beauty of this method is that you can selectively target localized hotspots. These hotspots are usually only a few hundred microns across, but with a laser you can focus on them and not waste energy on cooling something that doesn't need cooling. The idea has been around for about a decade. Already in 2012, researchers at the Niels Bohr Institute demonstrated that they could use this method to cool a particular semiconductor, gallium arsenide, down to just 4 Kelvin. Then in 2020, another group of researchers demonstrated that such laser cooling systems could be miniaturized and be integrated with microchips. This isn't going to be rolled out tomorrow, but it's a plausible and feasible method that could make a big difference within, say, a decade or so. And then maybe my laptop will stop sounding like a hairdryer, so I can hear myself grinding my teeth during updates. China wants to drill through Earth's crust, something the Americans tried unsuccessfully 60 years ago. And the Chinese aren't just doing it for fun. What do they hope to find there? Let's have a look. In the 1960s, the Americans had a bold plan. They wanted to be the first to drill through Earth's crust and into the underlying mantle. The mantle is normally about 35 kilometers down on land, but under the ocean floor it can be just 5 to 10 kilometers deep down. So they picked a spot off the coast of Mexico where the crust is thinner. The project was called Mohole. It's named after the Mohorovičić discontinuity, which is the boundary between the crust and the mantle. They began drilling into the ocean floor, but in 1966, after reaching just 183 meters below the seabed, the project was cancelled. It was too difficult and too expensive, and no one besides scientists was really interested. Now the Chinese want to do it for real. And they've got experience. Just 2 years ago, they began drilling a 10-kilometer deep borehole on land in the Tarim Basin. Why? Likely oil, because if you drill 10 kilometers down and find a McDonald's, you don't get to keep the burgers. But China imports about 20% of its oil, and the Tarim Basin is one of the most promising regions. What makes it unusual is not that it has oil, but how deep down the oil is. This basin has a continental crust buried deep under sediments. As a result, oil that would normally be found 2 or 3 kilometers down has ended up more than 8 kilometers below the surface, so they had a good reason to drill. The project began in 2023 and just finished in February. It reached a depth of 10,910 meters. That's still somewhat less than the deepest hole in the world, the Kola borehole in Russia, which is a little more than 12,000 meters deep, but the Chinese might well break this record with their next project. For this, they've built a new ship called the Mengxiang, which means dream stream. It's designed to remain stable in one location and then lower down a pipe in segments and drill until they reach the sea floor. From there it can drill more than 10 kilometers deep, and that should be enough to reach the mantle. If the drilling is successful, they'll be the first country to ever reach the mantle. That'd be a major scientific achievement, getting direct samples from a part of the Earth we've only ever studied indirectly. But this isn't just about the science. It's also a power move. We only ever observed less than 0.001% of the seafloor, but the ocean floor holds valuable resources, rare earth minerals, cobalt, and large pockets of methane frozen under pressure in pockets underneath the ocean. Getting there first means getting the first pick. It's also about geopolitics. In international waters, no one owns the ocean floor, so it's a race. Whoever drills there first has a claim to what they find. On April 24th, the Trump administration signed an executive order to fast-track deep-sea mining in both the US and international waters. They hope to secure critical minerals like nickel, copper, cobalt, and manganese from the ocean floor. These minerals can be found down there in so-called nodules, which are potato-sized clumps typically found at depth of 4 to 5 kilometers. The stuff is literally just lying around there. These minerals are critical for technologies such as electric vehicle batteries, wind turbines, and solar panels. Other countries, including Japan and Norway, are pushing for deep-sea mining too. However, the recent US push has upset some people because the United States signed an international UN agreement but didn't ratify it, which means it isn't legally binding for Americans. Had they ratified it, that would require them to seek approval for deep-sea mining. The Americans, in contrast, argue that, well, since they didn't sign the agreement, they don't need permission. China did ratify the agreement, but on some occasions it interprets it to its liking, especially for what their rights in the South China Sea are concerned. Environmentalists are worried that all this trampling around on the ocean floor will disrupt ecosystems, which it almost certainly will. But to be fair, the oceans are so big that it'll be a long time until humans have any sizable impact with their mining activity. So while the Americans want to pick up sea potatoes, the Chinese are opening an entirely new chapter, and they're writing it with a drill. Thanks for watching. See you tomorrow.